Yes.
So, good afternoon, Professor Velen, Professor Kumer, and Professor Luin. I welcome all the participants. A very good evening. So, sir, can we start now?
Okay, we can start. I would like to ask you to allow me to share. Initially, I will give some presentation and then I will give it to Uluin. So enable my sharing now, please.
Okay, okay, sir. I'll do. I'm doing it right now.
So welcome back. We have now a tutorial, and we will use this tutorial to cover one quite a specific topic, a problem that the energy supply technology is facing today. So I use this tutorial also for some particular to describe you some particular technological problems that we have to resolve in the future in order to live in less polluted and more sustainable environment. Now today we will talk about energy supply. Basically electric energy supply, about electric grid, about incorporation of renewable energy sources into the mix of our energy supply. So today's tutorial will look so that I will first tell you a few issues about that. I will illustrate the problems that we are facing and what can be consequences if our grids are not properly controlled. And then I will give words to my PhD student who actually is just about to finish his PhD, and he spent last 4 years in development of some technologies that can help maintaining stability of the grid, some innovative energy storage technologies. So he will take over from me, and at the end he will also show you a video of a system that illustrates how we can stabilize the grid even when it is supplied by a lot of renewable intermittent sources, like a photovoltaic cells and solar energy, which shines during the day but doesn't shine and doesn't produce any electricity overnight. So let me start with my little presentation here. So here we go. We're gonna talk about grid energy supply and how materials, new material technologies can help resolving the problems that are occurring in today's grid. Now I will first tell you two examples of these problems that can occur. One is from 2019, and it happened in the UK. You would think UK, they would have really well-maintained grid. But you see, even in such a country, something wrong can go on. Now, in this time in 2019, something's happened. It was a storm in the North England near Cambridge, and the lightning struck into the power plant. So the power plant went down. At the same time, also a gas-fired power plant nearby tripped. And simultaneously, the offshore wind farm shut down. So they were kind of lacking of about 1,000 megawatt energy in a very short time. And they couldn't substitute this with their reserves. So they were lacking 1,300 megawatt of energy in a short time, and they had only 1,000 megawatt reserve to back up this uh, all these power plants that shut down. So what happened? The grid, because of the lack of energy, the frequency in the grid fell down, and the blackout resulted. So it was long blackout over a vast region of England, causing millions and millions and millions of pounds of damage. So that is one failure that happened, and maybe you would still remember a year or two ago when there was such a snowstorm in Texas. They were out of electricity also for days because of these weather problems, which caused the shutdown of some producers, but also because it caused increased consumption of the electricity. So a little bit more interesting and to some extent humorous event happened. That was a little bit later, but it happened in Europe. So, and it is kind of political issue, really. I don't know whether you know, but the Serbia and Kosovo, they always have disputes. However, in Europe, our system of electric distribution is such that entire continental Europe, here in this little picture, it is colored in blue color, it's one grid. And if you have a shortage on one side, you can get power from some other places in Europe. But you have also neighbors that are the first who have to substitute your lack of production. Okay, so you see we have several such systems, but continental Europe is the biggest one, and then we have Baltic one, and Nordic one, and Great Britain, and then we have Ireland system. So here where we see Serbia and Kosovo, the situation is that Serbia must immediately jump in if Kosovo would produce too little energy. Now what happened? They got disputes, and Kosovo couldn't produce enough energy for themselves. So they had a shortage of energy, but Serbia, well, they didn't want to give them and to kind of fill up, their shortage. So nobody really noticed that because Kosovo's the production is minor compared to the whole European production, and nobody really noticed that because of this small lack of power in the European grid, what happened is that the frequency slightly was under 50 hertz, and that was going on for a long time. And then what suddenly we noticed that all our clocks on microwaves, or clocks that are running on and that are controlled by the grid frequency, they started to be a little bit slow all around Europe. And then they realized, oh, well, there is something wrong with the frequency in the grid, and they started to investigate what was going on. So at some point, all European clocks on microwaves and, I don't know, ovens and so on, they were 6 minutes late. Okay, of course, when they realize it, they fixed this problem, and now we got accurate clocks on our microwaves. Maybe you would now ask, why power shortage or lack of power influences the frequency in the grid. Now, I would like to give you one very illustrative example why this is so. Let's consider a cyclist. Okay. Now, the cyclist is riding his bike with a cadence, with a, let's say, frequency of pedaling 90 RPM, and he produces 200 watts. Somebody would do it more, somebody would do it less. But then, well, he gets tired, I guess, and his power goes down. So what happens when the power goes down? He can't pedal so fast anymore. So his frequency of pedaling drops below 90 RPM. Or maybe then he would drink some Red Bull and he would get this extra energy into his rings, so speaking, so he gets more power, and of course, this more power is more power happens that he can pedal with a frequency more than 90 RPM. This is pretty much similar as it's happening in our grid when the power is changing and the frequency is following. So now let's say so. At every moment in time, we have to manage the consumption and production of the electricity. So, and now what I'm showing you here is a typical production of the electricity over the day. Sorry, demands for the electricity, so consumption of electricity. Of course, during the night, we don't consume so much electricity, but we start switching on our lights or using our kitchen appliances in the morning. And then again, when we are at the work, we have some steady state consumption. But then when we go home and we do things, maybe warming up or cooling down our homes, it increases a little bit, and then in the evening it increases even more because we are all doing things, using our gadgets and all these things, and then slowly goes down to the night level. Now we have to cover these fluctuations by the production of electricity. Now here is a typical curve how we produce electricity. We can control the production of electricity, but we can't do it on such a fine scale which is required according to the consumption. So now we have to decide, are we going to produce electricity on this level as I'm showing you now, or are we going to produce it so much that we're going to cover all the peaks? But then what we're going to do with all of this electricity which is overproduced in other times of the day? Okay, maybe we can decide to produce the electricity just to cover like night levels, but then we got these peaks, and these peaks will cause blackout if you don't cover them. So we can do something in between, which is all fine, but still we have to take care, for these peaks. And we're losing some production here when the consumption is lower. So you see, we got severe problems in regulating our grid. Now, this is just another example. We have production, and we have overproduction, and we have underproduction. And now I put here T as a time, but I didn't put any unit here. Seconds, minutes. I didn't put any units deliberately because pretty much same situation is on the level, the order of seconds, minutes, hours, and even months. So always there is a period when we have overproduction or the period where we have underproduction. So we need to control and our grid at every moment and on the end every time scale. So therefore we have several levels of regulation, so that we can compensate this mismatch on very fine level. So it means on the second level, as you see here, for the first level regulation, and on more longer time periods. So first level regulation, that means on the seconds, when we have to keep the frequency within plus minus 1 around 50 hertz. It's a dynamic regulation which every energy producer must assure, so every power plant. And then we have second level regulation on a time scale of 30 seconds. And these are national system operators. They must have some infrastructure to do it, either batteries or pump hydro storage, or adaptable consumers that can adapt their consumption in a very high with a in very short time period. And then is a third level regulation. We have to respond in 15 minutes. But then here we are talking now already about large quantities of electricity, which we have to keep on reserve. And these are like some gas power plants, for example, gas power plants, but also pumped hydro storage can be the infrastructure for that. There are still other things. We need some reserves to assure black start. If we, by some accident, go into the blackout, then we need to restart our system. So we need reserves to start our grid in that situation. But there is one important thing which is still unresolved, and this is seasonal storage. Well, in general, well, it's valid more than for northern countries where we have seasons, not like when you approach equator, we don't have so much seasons that we have. We have snow in the winter and we have very hot weather in the summer. So normally in the summer we consume much less energy than in winter time. And in summer we have overproduction of energy. But unfortunately, we don't have a mean to store this overproduction and use it in the winter time. So this is still some unresolved issue. Now, and we are contributing towards resolving this issue, and maybe we can see on the horizon some of the solutions. So now all of this is becoming even more difficult to regulate when we are incorporating, adding into the grid more and more renewable energy. Why is that so? Look here, this below this plot here. This is a real power production from a wind generation, wind farms in UK in this particular time. So you see, at some point, this can be very high production when the weather is windy, but it can go very, very sharply down to zero in the next couple of minutes. And we have to compensate that all the time in the mixture of our grid. And you see that on the upper plot, you see that the share of renewables is with years, it's increasing and increasing. And these fluctuations, therefore, is causing more and more problem in the grid. So it's not all green and sustainable with renewables. We are meeting also some kind of serious problems, and we need really to work how to resolve these problems that are occurring now for future sustainable energy supply. Okay, now this was my presentation, and now I will stop sharing, and I would like now to introduce you to Ulrich Fluin, who will take over this and tell his story about the energy supply, and he will also present you what he has done and worked on during his PhD thesis. So Ulrich, please take over.
Thank you very much, Professor Valant. Hello to everybody. Yes, please let me share the screen so that I can show my story. Let's see the share button yet.
Hello, can you enable Louis to?
Yes, Professor. Yes.
Thank you. Yes. I guess you can see my first slide now.
Yes.
Can I give some feedback, please?
Yes, it is visible.
Thank you very much. So, yeah, once again, my name is Uroš Luin. Matjaž gave a great introduction to the next continuation of the story. So, the title that I put it is Why Renewable Energy Sources Depend on Energy Storage Technologies. So, first of all, I will tell you my background is in environmental engineering. And as you heard, now I'm a PhD student of the program materials, and I'm working on energy storage. So my task, my goal today is to present you where are the main problems and how we can overcome this and why is this required. So first of all, as you already noticed, we will talk just about stationary, long-term, and high-capacity energy storage technology, not about technologies for the electronic devices and for the e-bikes and e-cars, but just for the grid. So I will just give you first an introduction.
Just put your microphone closer.
How please? How please?
Put your microphone closer. We are losing you.
Oh, sorry. Yeah, I have very close to my face. I hope that now you can hear me better. I will try to talk really slowly and loud. So here's the first example of one very good country, good in the sense of renewable energy installation. So Scotland, here on the picture you have Scottish wind farms, and here on this partially blurred map you can see how many wind farms they installed, and they are going to install even more of them. And recent data already showed that just in 10 years they get rid of coal and oil, and they triple the amount of renewable energy sources, basically from the wind. And this is the left chart. And in the same time period, last 10 years, you can see with the gray bar, the renewable output. So I will tell you in short, the energy consumption is approaching 100% of renewables. So basically, in an average year basis, they are self-sustainable from renewable energy.
Please, microphone closer.
Oh, I don't know how to fix this. If you give me a second, I will try to improve.
Now it's better. Now it's better. Okay.
It's better.
Yeah.
I will try to put it like this if it works. I will hold with one hand. Okay, so like I tell you, and like it's written here, so they produce per year twice the amount of electricity they need for them needs, so for them households. But there is one big but. They were not continuously self-sustainable from renewables, so from renewable energy sources. And why? This question we will solve now in next steps. So simple answer is because they don't have enough energy storage capability. And first, let's do a step back and see the global picture. So how the world electricity production by source is done. So currently, I made this chart, I simplify it, I took the data from International Energy Agency, it's from 2018, and I grouped together fossil fuels, nuclear sources, and renewable sources. And as you can see, why also Professor Valant said that it will be the problem of the future, because 65% of currently produced electricity is done by fossil fuels. So we are generating majority of our electricity from fossil fuels. Just 10% is from nuclear power plants, and 25% is now renewable energy. So if we want to have a decarbonized planet like Scotland and other Northern Europe and also other countries are trying to achieve, we need to move globally all this big red share, and we need to distribute among renewables and nuclear. Here with nuclear, I have in mind fusion reactors if they will start to work soon. So if you now think a little bit, what are fossil fuels and what are renewables? Renewables are basically the energy that is coming from the sun to our planet. It could be direct sun irradiation. It could be a movement of air or water bodies, masses. And what are fossil fuels? Basically, they are also the products of sun, but unfortunately, they were forming, the formation was going on for millions of years, and we exploit them in too fast way. So they are not sustainable, and we will run out of them, and also they cause a major impact. But as I said, they are some kind of energy stored, some kind of sun's energy that is stored on our planet. So on the other hand, renewable energy, this perspective very different. So like Professor Vant already said, okay, Earth is majority populated in geolocations where there are present seasons. And first of thing that we need to solve that is not solved yet, so it's long-term energy storage. Practically, seasonal energy storage is not accessible yet. There is one simple answer why, and this answer is the energy, electricity is nowadays very cheap. I will give you two prices. So first price is the price of electricity here in Europe. It's close to 100 euros per megawatt hour. Same capacity batteries, lithium batteries, cost 3 orders of magnitude more, so more than 100,000 euros. So basically the cost of the electricity is the one that makes troubles to the economics and to the practical accessibility of renewable energy sources. But on the other hand, just imagine how nice will be and how environmentally friendly will be if we can store the summer excess energy and then release it in the winter. And here we are not talking just about electricity, but even cogeneration, so that we store energy and then we release it in the as heat and electricity. This is even better and very interesting for our decarbonization of the planet. But unfortunately, or as you already discovered, renewable energy sources are not constant. They are intermittent, and we have no control over them. And here are two plots. The left one is showing on y-axis power, and on x-axis the time. And the time is 24 hours, so a day. And this is something typical that it happens. You have peaks of overproduction and have peaks of demand. And like it was already explained by Professor Vallant, on any time scale from milliseconds to years, all we need to do, all the grid operators need to do is to match the load, so the demand and the production of electricity. If they are not doing this, the frequency goes up or down. And now you already heard what happens if the production and consumption is not equal. So we got a scenario where these two are mismatched, and what this causes in the light scenario is that we have higher energy losses. The next thing is that we start to have unstable grid. Then the managers have huge efforts to stabilize this, and they need to do special tricks in order to sustain that frequency at target level. So the case one, as you can see here with the blue line, it's the wind production. The black line is the demand. On Y is power, and again we have time on X-axis. And this case showing two windy conditions. So electricity is overproduced. There is too much wind for the grid energy demand. And you can imagine now the wind farms and the grid in the Scotland, like this guy who is this musician of the pipe bag. So he have a lot of potential energy. He wants to sing, he wants to play the bagpipe, but simply the bagpipe is clutched. So something like that happened to the grid at that moment. And very short after that moment, we have another situation where grid is again unstable. And at that time, we have underproduction, so the wind suddenly stopped, the sun didn't come out yet, and what happened? We have not enough power into the grid, so our frequency is going down. And you can see here two such scenarios, because typically we have two peaks, like you already saw in the previous presentation of Professor Valent. And unfortunately, the sun shines in between those two peaks. And of course, there we have also a third scenario when the sun comes out, it have a huge ramp, and in a very short time, we have all the solar panels producing full power, and now it's too sunny for the grid, so electricity again is overproduced, and again, we are losing the target frequency. So what's the solution now? What we can do? Again, we can employ energy storage. We can develop smart energy storing technologies that simply allow to store the excess production. So we are charging up our batteries. We're storing energy when there is surplus energy. And minutes after, when the grid needs electricity, we release that energy that was previously stored. And this we are doing all the time. So just imagine some controller that just controls, that monitors the frequency and just controls the such smart technology that can store and release energy based on the grid frequency. Like I said, we have plenty of already mature or already known or development technologies that can store energy. And here I marked with the green intermittent line those which are possible to use for long-term energy storage or mid-term energy storage. So those who are able to store enough capacity and can delay this storage. So first of all, hydrogen storage is one of them. In combination with fuel cells, this is a great candidate for the future. Synthetic natural gas is also one that can do that. Pumped hydro storage plants, we will see later. I will present a few of them. One of them is pumped hydro storage plant. Compressed air, this is something that is now emerging. It's emerging even underwater storage of compressed air, even liquid air or cryogenic energy storage. And also thermochemical processes are being developed. And if you search the web, you will see that recently many different technologies or approaches for grid energy storage and management are emerging and are under development because we need them. So there is also one alternative to the energy storage, and this is supergrid. So what supergrid means? Basically, this is a worldwide interconnected network. So a grid like we have in Europe. By the way, our European grid is a very good one. It's very interconnected, and we, as countries, collaborate very much. So we help each other to a certain extent. But yeah, it's the biggest grid on the planet that works synchronous. This means that, like Professor Valent said, everywhere you check the frequency that European grid, you will find pretty much the same result. what's the benefit of supergrid? So if we interconnect the entire planet, we make from renewable energy sources, like it's sun, we make a continuous energy source because we interconnect day and night, and we interconnect summer and winter. But unfortunately, this is not going to happen soon. Here there are some dates that are showing 2070 year when this supergrid will see the light. So until that time, we need to rely on some kind of energy storage, like it's pumped hydropower storage, which is the most deployed. It covers more than 95% of its installed global energy storage capacity. And it has advantages, of course. It's mature, it's clean, have no emission, have low operational and low maintenance cost. It improves power grid stability, but it has also drawbacks. So requires several geographical conditions. Just imagine you need to pump water uphill and then downhill, so you need to have hills. If you have a land where it's everything flat, you don't. You cannot install such technology. Also, you need water, so some source of water. And what else is a drawback is a big land footprint, relatively low energy density, and very high initial capital costs. And in the end, even if the round trip efficiency is quite high, we finish with very low energy density. And in Slovenia, we have one pumped hydro storage plant, which have had or falling height of the water from the accumulation lake. That this accumulation lake have 2 million cubic meters of water. Then you have 500 meters of fall, and then you have the generator. And this generator works when you have excess energy, like a sink of energy. So it used excess energy from the grid to pump water uphill and to fill up the lake. And then when you have the situation when the grid requires energy, so where there is the demand, you just release that water and you generate electricity that you pumped that you deliver to the grid, and you stabilize the grid in such a way. To give you a flavor of how big is this pumped storage plant, it's about 1/4 of our nuclear power plant. Or putting this into the numbers, the maximum power that this pump hydro storage plant can provide is 160 megawatts, and the energy that it can deliver is equal to fully charging up 25,000 electric vehicles, like Tesla S with a big battery. So quite a good energy storage. Something that works on the pretty much similar way, so also by gravity, but without water. This is the company from Switzerland, Energy Vault. I know that in India, the company Tata have such energy storage for them company, and it have several advantages, but unfortunately also some drawbacks. Again, we see that it have low energy density. But first of all, let me explain how it works. It's just a set of cranes. As you can see, 6 cranes that are just elevating concrete blocks that weigh around 40 tons each. And when actually this state is empty and you have excess energy, and you are just piling up your concrete blocks, and this state represents fully charged system. And the questions that you can see, so the drawbacks that you can see around the scientific and engineering debate is how this can charge up when there is strong wind. Do the cranes work when it's strong wind and you need to store the excess energy? And also, what if the land is happens some earthquake? So here I make a humorous way, so it would be super fast discharge if some earthquake will come. But anyway, it's quite good technology for store certain amount of energy. The other thing that also works by gravity is, let's say, pump storage on rails. This example is from USA. What they are doing, instead of water, they are running up and down trains that are basically, again, concrete blocks, and again, the same principle. When you have excess, you run down, you run them uphill, consume the energy, you stabilize the grid by using that energy, and when the grid requires energy, you let them down, you generate electricity. That way you stabilize the grid. Still, we have the problem of low energy density here. So we need a lot of such hills with such railways in order to store some decent amount of energy. And also, of course, you need to have certain land that have such hills. So again, in the flat area, it's not possible. Next thing I want to show you are the redox flow batteries. These are electrochemical devices that operate in a pretty much smart way. So you have two compartments and you run two different electrolytes. And what are you doing to store and to discharge is that you just move electrons through the membrane separator from catalyte to anolyte for charging up. Then you store that catalyte and anolyte in some huge tanks or some, like you see here, salt caverns, caves. And when you need the energy, you just pump up and the process is reversed. So you generate electricity. Then if you think about energy capacity, so the amount of energy you can store in such a system, it depends solely on electrolyte volume. So bigger the volume you have of the tanks, more energy you can store. And if you want more power, you need to increase your system. So bigger is the electrode surface area. Sorry, bigger is your electrode surface area, then bigger power you will have. Still, the energy density here is 10 times bigger than the previously shown technologies, but here are some other technical problems. Anyway, there are plenty of different chemistries that run redox flow batteries, and several of them are also deployed and already operational. And next one is the hydrogen, green hydrogen from water electrolysis. We can do that in several different ways. There are several different electrolyzers from alkaline to solid oxide. So the basic idea here is to use the excess energy again to split water into hydrogen and then store that hydrogen. But in order to store that hydrogen, we need also to compress it. And of course, when we compress the hydrogen, we lose some energy, and also we lose some energy while the hydrogen is stored in tanks. And now if we think from the perspective of long-term energy storage, if we store this energy in summer, before winter, we will lose a lot of hydrogen through diffusion losses, or self-discharge, we can call it, because the hydrogen gas escaped the tanks. He moves through, he diffuses through the metals and also makes some hydrogen embrittlement, so damage the tanks. And this is some kind of problem and also losses, energy losses connected with this technology. So at the end, we will find that such technology have overall efficiency from 30 to 40%, which, by the way, for such energy storage in the present state today, we are curtailing a lot of energy. So I will give an example from California, US. They installed a lot of solar cells modules, and nowadays what they do when the sun is too strong, they need to shut them down because they have not enough interconnected grid. They cannot send the energy on the other side of US, and they have also no energy storage capacity. However, hydrogen storage also presents some hazard because of cryostatic burns and explosions that could happen. But in the end, if we compress the hydrogen to 700 megapascals, we will get quite good energy density. As you can see here, 1,500 watt-hours per liter. So the grid regulation stage, Professor Valent already described them very good. What I want to add here is just based on what you saw now. So the first and second stage is already covered by the technologies that are already present, mature, and developed, and exist, and they are already used to do the first and second stage of grid regulation. But for the third stage, we want to get rid of these gas power plants. We want to use hydrogen or some other renewable source instead of fossil fuel. And yeah, we want to prevent unstable grid. We want to prevent blackout. And of course, we want also to have enough energy stored if anyway this happens, that we can again set up after the breakdown the grid so that we can do the black start. We now sum up what we told until now. So, and we ask ourselves, what objectives should cover an ideal novel energy storage technology for grid energy management? So how should look like? So first of all, it should improve the grid stability and flexibility. It should allow fluctuation smoothing. So like I already said to you, so peak shifting. It should allow long-term energy storage, so in order to enable seasonal storage. It should allow higher share of renewable energy sources in the power mix, and it should provide backup energy, like we already told. And all this, it needs to make for as low as possible price, or as you can see in the literature, the ratio between energy stored over energy invested. And those were also the objectives that we took in account when we were designing such novel energy storage technologies. That one of them, I will also present now to you. So here is the part solid technology that is now under development in our laboratories. And this is the main cycle. So first, if I explain the name, it's PTEC. So this means iron thermoelectrochemical cycle, and how this cycle store energy and stabilize the grid. I will show you in the next two slides, where I will split this cycle into two scenarios. So the scenario when we have excess energy, and in the scenario when we have demand for electricity. So let's reveal this. We have, let's say, noon. The sun is shining. We have also wind, so there is a surplus of energy. What we do, just use this excess energy to electrolyze iron that is in higher oxidation state. So we basically reduce the iron ions, cations, back to iron, as we know from every day. So metallic iron with zero state. Basically, we get as a product a solid material that is metal. So you can think about iron powder. And what we do to this iron powder, we just take it. We are just taking it out from the system, and we are storing it in a warehouse. Second thing that we are doing with this excess energy is the thermal decomposition of iron chloride. What we get HCl acid. So this HCl acid is a liquid that we can store in a tank. And now what we have two materials that are individually stored in our storage space. And the next step is, so when the electricity is in demand, so when we need the electricity, is to trigger the spontaneous hydrogen evolution reaction. And this reaction is so simple. We just mix iron and HCl acid, and we get hydrogen gas. So we get the hydrogen gas on demand. We are not storing hydrogen. We are storing iron and acid, and this can be stored for a long time without self-discharge, because nothing will happen to acid and to to iron. So we can have it there for 6 months. Nothing will happen. When we will mix them together, we will get hydrogen on demand. And what we will do with that hydrogen, of course, we will run it to the, we'll let it to the fuel cells. Fuel cells will produce energy, and that energy will stabilize the grid. So the second product is iron chloride. This iron chloride we already told that, yeah, we will thermally decompose it back in the next storing cycle. This is another slide where it's showing the same technology, but in a bit different way. So here is our laboratory pilot unit where we electrolyze iron cations to the solid iron deposit. On the other hand, we get acid. And what is here important is that from 3.5 liters of iron, we get, when we trigger this hydrogen evolution reaction, we get 11 cubic meters of hydrogen gas. And this 11 cubic meters of hydrogen gas, it's equal to 1 kilogram of hydrogen. And 1 kilogram of hydrogen is equal to 39 kilowatt hours of energy. And if you do this simple math, you will come out with energy density of 11 kilowatts per liter. So this is something equal to oil, and it's 10 times bigger than pressurized hydrogen gas. Here, this green, this is iron chloride. So if you think about sodium chloride, the salt that you use in the kitchen, iron chloride is also the salt. When it's solid, is a green solid material, and when you dissolve it in the water, it makes such nice green solution. So most probably now you are thinking how this hydrogen evolution reaction goes. If you want to see it, we prepared one contribution for our national television. So if you go with your mobile phone over this QR code, it will directly link you to the moment when we are showing that reaction. Unfortunately, it's in Slovenian language, but everything was already explained to you, so you can watch how tense is this reaction and how much hydrogen in so short time is generated from this little amount of iron. So the reaction, as we already told, we need iron and acid, and what we get is hydrogen and also heat. So basically, we are talking about cogeneration. So we are generating heat and the energy carrier, which is hydrogen, that can be further converted to electricity. And how we can control this reaction? There are many ways how we can control it. We can control over HCl concentration and dosing rate. Acid. We can adjust iron particle size. We can adjust temperature, or by pressure. So there are many ways how we can have control over this production. And we can also fully stop the reaction if we just rise up the iron powder from the acid by, let's say, electromagnet or classical magnet. Simple as this. And this brings me to the conclusions. So if we summarize all that we told to you now, we can describe this in one sentence. So we want the transition from fossil fuels. We use the fossil fuels to develop ourselves, to develop our modern society. But now we need to enter into the carbon-free era. And to enter the carbon-free era, we need appropriate technology that enable smooth use of renewable energy sources while keeping the grid stable. And I present to you one way of use of the power-to-solid technology, which is basically a materially closed circular process for storing energy. And the energy in this case is stored in the change of oxidative reductive potential of the metal. In the particular case was iron. So the main advantages of this technology are that we are not storing hydrogen gas, but we have stored material, so solid material, And when we need hydrogen, we trigger the reaction and we produce hydrogen on demand. And while the materials are stored, we have no self-discharge. This allows long-term storage. And since the charging and discharging unit is locationally separated, we can make it high capacity. Basically, our energy capacity is dependent only on our storage room. So if our storage room is full, then we build another one and we double the energy capacity in a cheap way. And because you noticed and you saw that the materials used are very cheap and abundant, these are iron, water, HCl, iron chloride. So this means that also energy stored in such a way will be cheap. And now it's time to show you this video. I hope it will work. Otherwise, you can also go over with your QR code reader and you can watch it later or again if you want. So what this video will show you, I made a control unit that combines the renewable energy source from solar cell module, and it combines power to solid energy storage technology for some kind of smart unit that can run the grid solely from renewable energy source. Here is nothing else attached, just this photovoltaic module, and here we have storage of our acid, which is here in the pump, and our solid iron is already in this reagent bottle, which represents the hydrogen reactor. This is the hydrogen fuel cells, and this is the control unit. But the video is self-explanatory, so you will be able to read and to understand, especially with all the knowledge that you got now. Yeah, we try to run this. First is the presentation of the parts and components. And now our three case scenarios. So first scenario is that we have a stable grid. So the sun is shining just enough and demand. So demand and production is matched. We have no surplus energy, we have no demand of energy, so the grid is stable. The little fluctuations are covered by some short storage or short or stage regulation facility. Now is the situation when it's noon in the summertime. We have overproduction from the solar cells. The system does. First, he identified that the frequency is going up, so that surplus of energy. Second thing that it does is that it starts to store the energy. And then we have unstable grid when the frequency is going below the target one, and this happens when we have some cloud over our region or during the night. The system does is activates and triggers the reaction. It generates hydrogen, and fuel cells generate electricity. And with that electricity, we stabilize the grid. These little bubbles, this is hydrogen. Yeah, the final final scenario is the stable grid. Okay. Okay. And with this, I will thank you for the great audience, even if I can't see you. And here I encourage you to check again these QR codes, and you can find some more information about our research that's going on. These are our papers that we published just recently. So thank you very much, and see you in the renewable future.
First, thank you very much for this presentation. Of course, if you will check out these videos online, it will be much better quality as it is now over this WebEx platform. In any case, I hope you have got an impression about the problems that we are encountering during the energy transmission and distribution. Now, what you were also able to see is that not all technological problems are resolved yet, that we do have some deficit in our solutions, which is obvious when we are talking about the storage of energy. Now, there were some ideas that we can use batteries for long-term storage, for seasonal storage as well, but that is more commercial hype than anything else, really. Namely, batteries, they have not good enough capacity, to accept all this excess of energy that we are occasionally producing. Well, just to illustrate that, I can say that occasionally it happens that the energy in Europe has got negative price. So that happens in the windy, sunny day, even a production of renewables is very high. We don't consume all of them, and we have to take care for this overproduction. And what happens on the market is that the price falls down to negative values. What it really means that you are paid if you consume electricity. So if you would have good consumer of electricity, you can earn some money with that. This happens occasionally, but it gives you an idea that these problems are serious and that it is worth to consider them, and we need to work on these technologies to resolve these problems. Now, I would like to challenge you with this, to think about joining later when you finish your studies, and if you have an ambition to become an engineer or some scientist, to join efforts in developing sustainable technologies. I would also like now, to give you a chance for discussion on that topic, which concerns all of us and everywhere on this planet. So I would like to give a lot of time for discussing this issue with you. So if you have something to say, if you have a question or a comment or anything, go ahead, tell us, write down in the chat box. Just let us know what are your thoughts on that.
Thank you, Professor Valent, and thank you, Lynn, for such a nice demonstration by the video for this completely renewable-based grid system. So here I have one question from Priyam Srivastava. He is asking that what is the concentration of hydrochloric acid used during electrolysis of iron?
Yeah, I will take over. Basically, during electrolysis of iron, we don't use HCl. acid is used for the hydrogen evolution reaction. So in the stage when we are releasing the energy. And concentration, basically any concentration, we can start with very high, and the hydrogen evolution action will continue until we have 0% of HCl in the solution. Of course, the rate of hydrogen production is strongly dependent on the concentration, but this is some kind of engineering. So with the proper engineering and design of the system, you can control this production of hydrogen. Hope that I covered the question.
I have one more query. On slide number 24, as you have asked that this iron 2 plus or 3 plus, when we have charged it by 3 plus or 2 plus, means transition state में
Basically, we have several approaches and also several deviations of technology. In some case, we go with 3 plus, in some case with 2 plus, but the idea here is just to use that difference in oxidation state for energy storage.
But my question is regarding the storage of this electrolyzed iron. Storage of electrolyzed iron, because iron is very much active in atmospheric condition, like it gets oxidized in normal atmospheric condition. If we have to produce a large energy storage system, then we have to look for this storage of this iron 2 plus or 3 plus in in
Yeah, we are storing iron in metallic form, so iron with 0 state. So iron, as we know it in everyday's life, of course, it have a tendency to rust, but it's properly prepared and stored properly, so not on rain, and in proper warehouse where also you can flush a bit with nitrogen. Nothing will happen with it. It can stay.
The idea is to store the electrolytic iron, to store it in some cartridges, in some vessels where we can flush air out and substitute it with nitrogen. So in that case, no oxidation can happen, and we can store it for a very, very long time without any damage.
Yeah, thank you, Professor. Here, one participant want to ask. He has raised his hand. I am unmuting him. So, yes, Mr. Puraram, you can ask your question.
Yes. Is my voice audible?
Yes, yes.
Yeah. Thank you, Professor Valland and Louis. A wonderful talk. My question is related to sodium ion storage. How you compare sodium ion storage batteries with your iron storage technology?
Yeah, well, you see, we don't want our system to be competitor to the batteries, because they can substitute each other and they can work together, and with proper engineering we can combine these two technologies. First of all, our technology will assure a high capacity storage capacity, while batteries would provide fast response time. With our technology, we still need some time, to generate enough hydrogen, and then through that enough through fuel cells electricity, while the batteries have got much faster response. So these two technologies have got different parameters, different characteristics, and with a smart engineering, we basically can combine these and produce some storage installment that will satisfy what we need today in the grid, and we need large capacity and fast response time.
Okay. Thank you. And that means generally for prompt response, your technology will use in that direction.
This technology will use for great amount of energy, yes, for large amounts. We are talking here megawatt hours and on.
Okay. Thank you, bro.
Come.
Professor, I have one more question. Like, if we talk about this frequency unbalance due to uncertainty of or irregularity in this non-renewable sources like wind and solar, these are particularly time-based energy systems. So, like we can use this pumped storage hydro plant because as per the literatures I have gone through, this is the best suited solution for this mitigation of unbalance of power or mitigate to extra load requirement in of peak hours.
I didn't hear really everything what you were telling me now. The
I
best,
would
what have you read about best solution?
yeah, pumped storage hydro plants.
Oh, yes, it is. It is very good solution. I mean, it's a very good solution. It has got high efficiency. However, it is not available everywhere. That is the problem, because you need you need altitude difference. You need hills, mountains to install this kind of storage facility. And now, for instance, let's take the Central American plains. You don't have any mountains there. You know, they all start with the Rocky Mountains, but miles and miles before towards east, there's no mountains. Northern Europe, like North Germany, there's all plain, in also North France, and so there's all plains, and you don't have these facilities available. And for instance, I will tell the story what is happening in China. The most of wind farms in China are allocated in the inner Mongolia region, and this is just the plain. And there's nothing, no possibility to build the pump hydro storage. So what is happening there is that they have a serious problem how to get all this produced wind energy into the grid, and Chinese government for now stopped any further construction of wind farms in that area. So you see, although we do have good option like a pump hydro storage, we cannot apply it everywhere. So this is the problem with the pump storage.
And what if we talk about the compressed air storage?
Well, yeah, you know, that are really more experimental facilities with compressed air, because you know you can't really get a high capacity with the compressed air. They have even idea to compress air into the old mines. You know, but the recharging of these systems is extremely high. So you're using a lot of air through the walls of the mines. And if you think of producing tanks for the compressed air, you will never get a lot of capacity, storage capacity. Of course, look, also the message that we wanted to give today is that we do have a lot of storage technologies available, but there's no ideal storage technology. You know, they suffer some drawbacks, you know, like they are not available on every geographic position, or they have low capacity, or they have extremely high price, or they, you know, uh, there are many of them also in very experimental phase, like hydrogen storage. Hydrogen storage is also quite okay, you know, but would you really like to have in front of your house a big tank of compressed hydrogen? And you will never know what will happen next day, whether it will blow up and your house with it. So you see, we will have many technologies to combine in future for that purpose, not only one.
Thank you so much, Professor. And one more last question. Is there any progress in the world where the peoples are looking for this super grid concept? Or is the
Of
world
course,
moving?
the world is going toward this. This is the debate that's it's going on for a long time. It's not from today. Also, if you check our European grid, it has such a concept. We have a European super grid. We are interconnected. The problem is that we are small Europe. We are not covering day and night. But yeah, that's the idea now. So that we, with the European grid, we go to the Greenland, and also US, it's coming to the Greenland from the other side, and then we meet there, and then we interconnect this. Already there are some attempts to interconnect Europe and Asia, and you saw the date, 2070. So if we manage to do that, then we solve majority of the energy problems. Even if the fusion reactors will work one day, there will not be many. There will be the early stage, just few of them, and we need some strong grid to also to get energy from them. But here with the super grid, as you can see today, even in 2022, we have war or almost war on the planet. So super grid, it have one problem that is more orientated to politics and some other things, not to technology.
So let me add something about supergrid. The problem of supergrid, and not only supergrid, but all long distance energy transport, electric energy transport, is in losses in the copper cables. Now this is, of course, getting serious if we are considering long distance energy transmission. For that reason, for instance, we could also ask ourselves, why don't we have, like in the Sahara Desert, why we don't cover it with solar cells, and then, just on the cables transport grid into Europe or Asia or whatever. The reason is that still on such a long distances, there's too much losses, conductor losses in a copper cable. And for now, and yes, of course, we are talking about AC current here. Now, the ideas, and also people are developing DC networks, high voltage DC networks, which would reduce this long distance conductor losses. Maybe Uroš, you know more about it. Maybe you can say something about the DC networks.
Yeah, correct. The DC, high voltage DC networks, these are the ones that are believed to be used in the supergrid. They have much lower losses when you go over 1,000 kilometers, so compared to AC grid. So, but still you have losses. But anyway, I think that the number is around 4% per 1,000 kilometers. So, but if you now consider our planet, so we have 40,000 kilometers go around. Let's divide by 2. Yeah, we have certain level of losses, but still, it's some idea how to transfer the day and night production, so day production to the site geolocation where there is night. Of course, with certain losses and technical issues.
Okay, we still have time, so if you got more questions, go ahead. I see in the chat. I will read this in the chat. If we talk about clean energy, the nuclear energy comes in the list. How nuclear waste is utilized? Okay, yes, we consider nuclear energy rather than completely green energy. We consider it as emission-free energy because it does not emit carbon dioxide, so it's carbon-free energy. But it's coming towards sustainable energy also with the new nuclear technologies. Namely, new nuclear technologies are developed in which you can use the used fuel for the new cycle of the energy production. Or if you use like thorium, if you use thorium as a fuel, you don't need to undergo all this thorium isotope purification, because the thorium is activated by itself within the reactor. So we can't say, of course, it's perfectly green energy. But with respect to the environmental burden, it's much better situated than, let's say, fossil fuels, for instance, or even natural gas. So therefore, we can, of course, say that the nuclear energy comes close to sustainable source of energy. There's a lot and enough of uranium in our Earth crust. For now, I mean, we need very little of this uranium for the power plant, nuclear power plant. Now we have to resolve properly the nuclear waste, of course, storage. So if it goes very, very deep underground, it's still acceptable, it's still good. But of course, the crucial thing is to assure the safety of the nuclear power plants. Unfortunately, I'm sure you are aware of a couple of accidents with very, very tragic outcome. But if we do assure the safety, well, with the nuclear very close to sustainable source.
Thank you, Professor Valent. I hope you are clear with the answer. Priyam, if you have any query, you can raise your hand or you can post in the chat box. So right now, Professor Valent, we don't have any more questions from the participant side.
Okay, then we can close this tutorial today and meet tomorrow for the lectures again. Okay, bye-bye, good afternoon.
Thank you.
Good
Bye bye.
afternoon.